This video is about Chapter 5, which talks about energy starting from collisions and interactions and then building into different kinds of energy and conservation of energy. So the background again is to first look at collisions. So we'll use the same kind of image that we've used before in Chapter 4. And then define kinetic energy, talk about examples of different collisions, and look at conservation of energy. So our quick review is our momentum equations that we've been working with. The momentum concepts have to do with relating velocity, changes in velocities and inertias, defining momentum, looking at conservation of momentum for an isolated system, and then also the momentum law for systems that are not isolated. So you'll notice these little key words like isolated system or closed system as we continue through these different kinds of interactions. And these are actually important words. Think about when you use them and when you don't. So we're going to do some new definitions here. We've got we're getting towards relative speed. So let's start with the definition of the relative velocity of two carts. The relative velocity, called v sub 1, 2 with a vector symbol, is simply defined as the velocity of 2 minus the velocity of 1. So it's just the velocity of cart 2 relative to the velocity of cart 1. The relative speed of the carts is simply the absolute value of this difference in velocities. So let's look at what this means. And this is also not the same as the difference in the speeds. If we look at this image on the right-hand side here, we start with a relative velocity of the standard cart of like 0.42 or something like that, and a relative velocity of the other cart of 0. So the difference is approximately 0.4 between them. And if we say v unknown minus v standard, it would be 0 minus 0.4, and that would be minus 0.4. Later, if we looked at after the collision, the velocities are minus 0.2 and 0.2, so we have the difference between the velocity of the unknown and the velocity of the standard is 0.2 minus 0.2, which gives us plus 0.2. So the relative velocities actually change in sign before and after the interaction, but the relative speed is the same. We got about 0.4 before and about 0.4 after. Absolute value of that gives us a positive 0.4 in both cases. Let's just take a quick look, though, at the difference between that and subtracting speeds. If we look at this post-collision situation and we subtract the speeds, which would mean the magnitude of the velocities, I would get approximately 0.2 minus approximately 0.2, which would give me approximately 0. So the difference between the speeds is actually not the right definition. So let's look at the relative speeds of these two carts. We just examined the two carts and we said in the case of the second situation, the relative speeds are in fact the same before and after, even though the change in velocity of the two carts is quite different. So the unknown cart doesn't change its velocity very much, and the standard cart changes its velocity quite a bit. So we want to ask ourselves what quantity that's related to the relative speeds can tell us that something has stayed the same before and after some of these collisions. What we're going to use is this quantity called kinetic energy, and that is the energy associated with motion, hence the kinetic part. So kinetic energy is defined as 1/2 mv squared, and the v is squared, so you notice that that it has to do with the magnitude of the velocity, since we're going to square it. The main point here is that in collisions where the relative velocities are the same before and after the collision, in other words, before the collision and after the collision here, the kinetic energy will also be constant before and after the collision. So let's look at these three examples and look at the relative speeds and then classify them, so this is introducing new language, as elastic, inelastic, or totally inelastic. In this first case, the relative speed is greater before the collision than after the collision. We call this inelastic. The kinetic energy is not conserved in this case. However, in every collision for an isolated system, momentum is conserved. Now, in this case, the second one, our relative speed is quite large before the collision and is zero after the collision. And we call that totally inelastic. Kinetic energy, again, not conserved. However, momentum is conserved because momentum is conserved in every collision for an isolated system. In this case, final case, this is what we call an elastic collision. And this is where the relative speed is the same before and after the collision. And kinetic energy is conserved. Momentum is also conserved because, let me say it again, momentum is conserved in every collision for an isolated system. So, in words again, an elastic collision is one in which the relative speeds before and after the collision are the same. An inelastic collision is any collision in which the relative speed after the collision is lower, or potentially higher if it's an explosive separation, than before the collision. A totally inelastic collision is a special type of inelastic collision where the two objects move with the same velocity after the collision, so their relative speed is zero. So an example, and this is out of the text, this is an example that you can find in the textbook in section 5.1. In this case, let's say we've got cart 1 moving along a track. At 1.2 meters per second, it hits cart 2, initially at rest. The relative speed is 1.2 minus 0, or 1.2 meters per second. After the collision, the two carts move at 0.4 meters per second and 1.6 meters per second. So the relative speed is 1.6 minus 0.4, which is 1.2 meters per second. And that's the same before and after the collision. That should lead us to a conclusion, which, in fact, here it is. Our conclusion is that because the relative speeds are the same, the collision is elastic. In the next situation, a piece of putty, our favorite little sticky thing, moving, I don't know how, at some initial velocity of 22 meters per second, hits a block moving at 1 meter per second, and afterwards the two move at the same velocity of 1.7 meters per second, and since the relative speed definitely changed, in other words, after the collision at zero, we can conclude that the collision is totally inelastic because the relative speeds are zero after the collision. So this is an example that you started on your worksheet, and in this case you have an inertia of 52 kilograms, for example, and you're standing at rest on an iced over pond in your skates. In other words, there's no friction and no outside forces acting on you. All of a sudden, your 60 kilogram brother skates in from the right with a velocity of minus 5 meters per second and collides elastically with you. So, before the collision, the relative speed is the difference between minus 5 meters per second and 0 meters per second, which is a magnitude of 5 meters per second. Therefore, after the collision, the relative speed will also be 5 meters per second. We can use that to find your final velocity. If your brother's final x-component of velocity is minus 0.36 meters per second, your brother's velocity increased from minus 5 to minus 0.36. So your velocity must decrease from 0 to a negative something. The negative something is 0.36. It has to have a difference between itself and 0.36 of 5. That sounded quite complicated. You should write it as an equation. So our final velocity is minus 0.36 minus 5, which is going to give us minus 5.36 meters per second. And we would hope, since we used part A to answer part B, that our answer would be consistent. But you could also do it by using change in velocity of B relative to the change in velocity of A. So our final answers to accurate significant figures are that the relative speed is 5.0 meters per second, and the final velocity of U is minus 5.4 meters per second. Right, so we're back to our thinking about kinetic energy and then looking at examples. And this shows a link to find the collision lab. If you work at the collision labs, let's just do an example here. Let's take m1 equals 1 kilogram, m2 equals 2 kilograms, and the initial velocities equal and opposite magnitude and direction. All right, so our masses are 1 kilogram and 2 kilograms, and then we want to change the velocity. We just show more information. And here we want to make the velocity of the second one equal to -1. So we see the little arrows here show equal velocity arrows, different inertias. And we're going to make this an elastic collision. Let's also watch the kinetic energy. And we could also watch the momentum vectors. All right, here we go. We'll play the interaction and then stop it and see what happened. So our kinetic energy now is 1.5 joules. We started with 1.5 joules. That should not be a surprise. Our initial velocity is 1 and -1. After the interaction, our velocities are -1.67 and 0.33, which has a relative velocity of 1 again. Do that one more time. So we start here, you can see the inertia stay the same, the positions will change, and the velocities and the momenta will change. However, the sum of the momenta will be the same because of conservation of momentum, and the relative velocities will be the same because the collision is elastic. The PhET is a good way to check your answers for homework problems and even to substitute a number for answers, and then be sure that you can do it algebraically. All right, so we're going to do a little math here to explore more about elastic collisions. We started with the relative speed of two carts. v12 is the absolute value of v2 minus v1 velocities. And we also can actually observe that for an elastic collision, the relative speeds will be negative to each other. So v12 is minus v21. Notice here the indices changed. So the relative speed of 1 to 2 is minus the relative speed of 2 to 1. This is what that means. The relative speed 1 to 2 is minus relative speed of 2 to 1. The conservation of momentum says that our initial momentum equals our final momentum. And then when we put this together with a bunch of algebra, we find that these quantities are the same before and after the interaction. 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals the same 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Those quantities are clearly important. Just like we determined that momentum was important, now we've decided that that quantity 1/2 mv squared is important, and so we call it kinetic energy. The previous equation tells us that the kinetic energy before the collision equals the kinetic energy after the collision for a collision that is elastic. So, kinetic energy is conserved. And let's just make a note for units. The standard units for kinetic energy are kilogram meter squared per second squared, and we call that joules. All right, so our conclusion here is that for elastic collisions, kinetic energy is conserved. You can check this with particular examples. This is a good one to look through. Just look at the numbers and how they're being used and see that the kinetic energy of the whole system should be the same for an elastic collision and not necessarily the same for inelastic collisions. This is another example problem that has shown up in a couple of places, and let's just look through the solution to this problem. So if we have a cart moving with some speed v1 initial, and it collides with another cart at rest. Let's see what happens to the final speed and the kinetic energies. First, we want to look at the final speed by using conservation of momentum. So the initial momentum, one object moving, the other at rest, should equal the final momentum, identical carts, final one at rest. And we see by solving this for v final that 1/2 v1 initial equals v final. Now our kinetic energy before the collision is just the kinetic energy of one object moving, 1/2 m v1 initial squared. The kinetic energy after is 1/2 the total inertia times v final squared. Substitute for v final, and we find that the kinetic energy after is 1/2 m v1 initial squared times 1/2. So if we want to find the ratio of that, or the fraction of the initial kinetic energy that is in the final kinetic energy that is in the collision, we simply find the ratio of k final over k initial and see that it's equal to 1/2. This collision is then, again, not elastic. This is an inelastic collision, and that is the ratio of the kinetic energies. Another example you can do is to work through using diagrams the kinetic energies before and after collisions, and you'd find answers approximately like this. I'm going to let you look at this particular example, and the solution is here. Write it out yourself as an exercise. Start with this page, write it out, and then see what you come up with. See if you can find the solution. Let's just take a quick look at what happens when we double the velocity of an object, and remembering that the momentum is equal to mv. If we double the velocity, then the momentum will double. So we know it must be either answer A or C. And if we double the velocity, the kinetic energy is proportional to v squared. So the kinetic energy will increase by a factor of 4, and our answer is C. This is another example of looking at conservation momentum and energy. I think many of you might think, oh yeah, I can kind of picture what would happen. Here we have two balls moving to the right and one little steel ball moving to the left. And after they hit, you're going to see two balls moving off to the right and one moving off to the left. But what makes you know that for sure? Conservation of momentum says that we must have a difference of 1 unit moving to the right. In other words, the total momentum here is equal to 1 unit moving to the right. Because we have 2 to the right and 1 to the left, the difference is 1 unit to the right. So we could end up with 3 moving to the right and 4 to the left. Well, actually we can't. We could end up with 0 units moving to the left and 1 unit moving to the right. So why do we get this 2 and 1 situation? This would be the final situation, and the answer has to do with conservation of energy, that we also have to conserve energy, and that restricts our solution to needing the same mv squared final as we had before. So kinetic energy is a scalar quantity, and that means it doesn't have a direction, it just has a magnitude. So we can use bar diagrams to show what's happening to changes in the kinetic energy. In a collision that's elastic, you might start with some initial kinetic energy in one object, and then afterwards you have some kinetic energy distributed between the two, but the total must be equal to the first amount of kinetic energy. For inelastic collisions, that actually wouldn't quite be the case. There's this total here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 yellow blocks. And here we have 1, 2 into K1 and 1, 2, 3, 4, 5, 6, K2, which is 8 yellow blocks. So a little less kinetic energy. So where did that energy go? There was that initial kinetic energy that then wasn't there after the collision. And that is converted kinetic energy that goes into internal energy. And in this case, like we can think about elastic collisions where the kinetic energy stays completely, where the energy stays totally kinetic. But inelastic collisions are such that one form of energy is converted to another form of energy. Kinetic energy to internal energy. So we can say for inelastic collisions, the states of the colliding objects change. And this change in state means that their internal energies will change. However, for any collision the total energy of the two colliding objects doesn't change. Now, if we introduce a bar diagram for internal energy before and after the collision, they'll be equal. So we add up these blocks before, we should get the same number of blocks after. Here, same thing. We add up these blocks before, we'll get the same number of blocks after, even though now we have less kinetic energy and more internal energy. So all of this in equation says that the initial kinetic plus internal energy equals the final kinetic plus internal energy. And the total energy of a system is E equals K plus internal energy. So we can just rewrite the first equation as initial energy equal to final energy. And we call that conservation of energy. We could also make this statement if there's not other changes in energy happening. So this is what we've got. This whole conservation of energy idea is that energy can't be destroyed or created, but it can be transferred from one object to another or converted between different forms. In this particular example, you drop a ball into a mattress, the ball stops moving, so the kinetic energy changes, and the internal energy of the mattress increases because you're compressing springs or you're heating up the particles in whatever the mattress is made out of. And so there must be an equal amount of energy gained in that internal energy as there is lost because of kinetic energy. Explosive separations is another example where we have conservation of energy. And in explosive separations, we start with some initial kinetic energy of zero, and end up with a final kinetic energy. Also, we have the change in internal energy is equal to the change in kinetic energy. All of it adds to zero. And using those two things, we can find our final velocities, final speeds, and final energies. So let's do one example to finish up this long video. Common examples of explosive separations or of storing energy is using springs. Let's suppose we've got a cart against a compressed spring that's released. And we're going to do an example that has to do with that. This example comes directly out of your text. So you can go back and look, and I want to do this coming directly out of the text to show you what kinds of examples are there. Let's look at the picture. Initially, we're going to have two different situations. We're going to first compress a spring using a 0.25 kilogram cart, and then let it go, and the cart's going to move. Look at the bar diagrams down here. We initially start with no kinetic energy and some compressed energy of the spring. And then all of that spring energy goes into the kinetic energy of the cart, and we have no energy left in the spring. Now we know in the problem the cart's speed after it's released, 2.5 meters per second. Therefore, we know the kinetic energy of the cart. Therefore, we know the initial internal energy of the spring. Okay, next situation. We have two carts that are pushing the spring together, and the same amount, pushing the spring the same amount, and then they're released, and we want to find their final speeds. So what we know is the same is the amount of energy stored in the spring, and we can quantify it, give it a number, from the first situation where we knew the amount of kinetic energy after the carts were let go, and then relate it to the second situation. Okay, so again, the key point is that the springs were compressed identically in both cases. And in the first case, all of the spring energy goes into the 0.25 kilogram cart, and then the same amount of energy is evenly distributed. So we're going to first calculate the energy in the first cart. Okay, now let's look at the kinetic energy. The initial kinetic energy is 1/2 mv squared for the first cart, and so we find that the amount of energy we have to work with is 0.78 joules. So the energy stored by the spring is minus 0.78 joules. Next, using conservation of momentum, we can rewrite V1 final as minus M2 over M1 times V2 final. Plug in V1 final in for substitute in here for V1 final. So we have M2 over M1 squared, V2 final squared, plus 1/2 M2 V2 final squared. So this is our M1 term and our M2 term. Simplify that by multiplying both sides by 2M1. Then factor out the V2 squared and divide by M2 times M1 plus M2. And now our V2 final is equal to the square root of 2M1 delta E over M2 M1 plus M2. So plugging in numbers for this, we get a final speed of 1.0 meters per second. Who manages to make these problems work out so perfectly? All right, so if we put this into the initial equation, we find that V1 final is equal to minus 2 meters per second, V2 final is equal to 1 meter per second. So the carts do move in opposite directions, that's good. Cart 1 moves at twice the speed of cart 2 because it has lower inertia, and the relative M1 and M2 is actually irrelevant, so we can switch them around, and that gives us a good solution. So there we are, the end of chapter 5. Please review the text for these sections and keep working on homework.